This video is towards the fulfillment of deliverable 3.3 on mathematical framework for converter interaction modeling. Here we present the framework for reliable AC-DC grid operation. The presentation is organized as follows. First, we start with a short background on this topic. In the next section, the framework for converter interactions in reliable operation is discussed. Here, an implementation of a preventive corrective security constraint optimal power flow model for hybrid AC-DC system is shown. Finally, some test results will be presented. The N-1 criterion has been in use for reliability management by the system operators. However, this criterion does not capture the actual likelihood of the different contingencies in the power systems. And this may lead to scenarios with high operational costs or higher system risk. There are also increasing uncertainties in system operation due to the increased penetration of renewable energy sources, as well as due to the development of smart grid framework. Thus, there is a drive to move towards probabilistic reliability criteria. Out of the current approaches for reliability management, that is preventive security and preventive corrective security, the preventive corrective security approach provides for an opportunity for trade-off between the cost of measures taken and the system risk. However, a quantitative assessment of the trade-off between the measures and the system risk is necessary. With the increased integration of HVDC into the existing system and the planned development of HVDC grids, there will be fully controllable exchanges between the AC and DC grids. This flexibility from the AC-DC converter in terms of change of set points of active as well as reactive power could be utilized in the form of preventive measures in reliability management. As the time constants of the AC-DC converter are much smaller as compared to the traditional equipment in power systems, they could be used for fast corrective actions as well. Moreover, these actions are more economical than doing a generator redispatch or load curtailment. Thus, it is necessary to include and assess the impact of HVDC in the framework of reliable grid operation. In line with the framework for converter interactions in reliable operation, a preventive corrective security constraint optimal power flow model for hybrid AC-DC system has been implemented. The objective here is to minimize the total risk, which is equal to the sum of preventive redispatch cost coming from generators and AC-DC converters, and the corrective risk, which is equated to the probability of contingency times the corrective redispatch cost. In this case, the corrective actions are from generators, AC-DC converters, as well as load shedding. The decision variables for this optimization model include the generator active power redispatch, the converter AC side active power redispatch in the base case, as well as generator active power redispatch, the converter AC side active power redispatch, and the active power component of load shedding in each of the contingency cases. The equality constraints considered here are the AC and DC grid power flow equations, the nodal balance equations for the AC-DC nodes, as well as the power flow equations for the converter station. In terms of inequality constraints, we consider here the limits for the generators, loads, and AC-DC converters, the nodal voltage limits for AC-DC nodes, as well as the branch thermal limits for AC and DC branches. This model has been implemented by using the Julia Jump platform, and it is built on the existing powermodels.jl package, which is a power system optimization toolbox developed by the Los Alamos National Laboratory. It is also using the features from the extension packages of Power Models AC-DC and Power Models Reliability. As we can visualize here, the model is built of 3 stages. We start from a reference case, followed by a preventive redispatch stage, where we have the preventive redispatch from participating generators and converters. This is followed by the contingency stages, where for each contingency, based on its probability, there is a corrective redispatch from the participating generators, converters, as well as load shedding if required. Thus, the objective, as mentioned earlier, is to minimize the total risk, which is a sum of the first stage or preventive actions cost, as well as the second stage risk, which is the probability times the corrective actions cost and the load shedding cost. This model was implemented on a 67 AC bus system, which is actually an AC HVDC overlay system. 13 critical contingencies were realized in this case. At first, the impact of contingency probability on the preventive corrective redispatch was analyzed. It was seen that as the contingency probability increases, the total risk also increases. It is also seen that with increasing contingency probability, it is more favorable to go for preventive measures and thus higher preventive cost or first stage cost than the second stage risk. Another impact that was analyzed was of the AC-DC converter corrective redispatch. In this case, the tripping of AC branch between buses 2 and 12 was considered. Firstly, the preventive corrective redispatch was run, where the converters participate in both stages. We got a total value for risk, as well as a value of corrective risk. It was seen that there is only the redispatch of generators and converters in the second stage. However, when in the next simulation, the converters were not allowed to participate in the corrective stage, it was seen that there is a higher total risk, and now there is a component of preventive cost as well. Moreover, the generator redispatch in the second or corrective stage was also higher in this case. This highlighted the impact of inclusion of AC-DC converters in preventive and corrective stages of reliable operation. These are some references that were used to implement this model and to run the test cases.